Thank you very much. So now that I'm wired, we can start. Today I will talk about securing a system with AppArmor and SE Linux. And first I will give a short introduction about what we talked today. So first we will cover mandatory access control, because both of those systems are mandatory access control systems. Then we will cover AppArmor and SE Linux, which isn't surprising if you look at the title. And then I will give a short comparison. Oh, this is the old version. This is not the one I sent yesterday. Then we have to improvise a little bit, because this one is made for 60 minutes and I reduced it a little bit for 50 minutes, and even 50 minutes is short, so we will speed through this thing. So this talk will be a mix between concrete examples and high-level concepts. This is because both of those systems are very complex, and it's not possible to explain them both in 1 hour. And because of that, some of the statements that I will show are simpler than they would be in reality. So you can't take the examples for the profiles I will show and just put them into your system. That wouldn't work. So who am I? I'm a SUSE employee since this year, so I'm quite new. I'm a security engineer and currently resident in Germany, and I don't speak Swedish, so I didn't understand very much today. I have a long-time interest in IT security, and I'm a fan of mandatory access control systems, and especially those systems where you can control the access very fine-grained. So I started with RSB AC. I don't know if anyone of you knows this, but this was one of the first systems that was available for Linux, and this was available in 1998. And it's my first time in Stockholm. I have to say it's a very nice city, but it's a little bit cold. But nothing what, in comparison to what you will experience in the next few months, I think. So let's get started with mandatory access control, because it's probably not a term that everyone is familiar with. If you want to talk about mandatory access control, then it's useful to talk about discretionary access control first. This is the usual form of access control that you know on Linux. So if you list a file, then you see that it has an owner, it has a group, and it has certain permissions. This is nothing new for you, so I won't explain it. The main point here is that the word discretionary. So the owner of an object can control the access of the object he owns. So if root decides to give this file to someone else or make it world readable, then there's nothing that prevents him from doing that. There are some drawbacks with discretionary access control. First of all, it's pretty coarse, so you don't have many ways of controlling the access. Of course, there's stuff like access control lists and stuff like that, but basically you only have those 3 access bits, and you have them for the owner, the group, and everyone else. Next, it's prone to user error. So nothing really prevents me from making my own SSH private key world readable and writable. If I do that, then tough luck for me. Next, it's hard to analyze. So all the permissions that are spread over the whole system are spread over the whole system. There's no central way to analyze it. There are, of course, tools that can help you with analyzing those permissions, but you first have to use something like this. And then there's also the usual problem. Root is pretty much God on those systems. It's a little bit less problematic in the last few years with capabilities, but basically that still holds true. But we still use this because it's familiar, it's easy to use, and easy to understand. So I think everyone here in the room knows how to use the standard Linux permissions. So what is mandatory access control? The main difference is the first word, big surprise. And mandatory in this context means that access control decisions are not made by the owner or user, but they are made by a centrally managed policy where all access control rules are in one place. And this has several advantages. The access control is in the hand of people who know what they're doing, so probably you. And you can you can control them centralized, and you can review them if necessary. So for example, there are papers that analyze the SE Linux policies that are available, And you can show certain properties, for example, that it's not possible for secret data to leak out. And another advantage is that they are often very fine-grained. So you can compartmentalize information, which is quite hard with the traditional systems. But of course, there are also drawbacks. Sometimes they're a little bit hard to understand, and you will probably know what I mean by the end of my talk. They are sometimes complex to administer, which you will see once you try to run a SE-Linux system for a time. And the main obstacle is the missing support and the missing experience. So I don't know how many of you know AppArmor and run it. So not very many. And how many of you use SE-Linux? Okay, so there are some people, but very many people don't know it. So for the people who know this stuff, this talk probably won't be very interesting for you because this is introduction level material. So let's talk about AppArmor. AppArmor is a Linux security module, and it's part of the mainline kernel since 2.636. And it was originally developed by Emonix, which then was bought by Novell. And Novell finally bought SUSE, and because of that, it's the default system in SUSE, OpenSUSE, and also Ubuntu. Maybe there are more, but those are the systems that I know. The basic idea. First, a sip of water. You want to restrict the possible actions that a process can do. And how do you do that? You map a profile to a process using the path to the binary as a key. And we will see how this is working with the concrete examples that follow soon. Very often, AppArmor is only used for network-facing daemons. This is in contrast to SE-Linux. SE-Linux is used very often for pretty much everything on a system. You're flexible there. You can use it also for only network-facing daemons, but AppArmor is very often used only for network-facing stuff. It has a couple of advantages. First of all, it's relatively easy to administrate. And you will see that once we get to SE-Linux, there are quite good tools available for AppArmor that help you in your task of creating profiles. And of course, it's supported in SUSE products. But it also has a couple of disadvantages, first of all, and that's probably the main one. It can't do everything that SE-Linux can do. This is something that you just have to check. What do you want to do with AppArmor, and is it capable of doing stuff like that? So if you want to restrict possible network interactions and you want to do this very fine-grained, then probably SE-Linux is better for you. And also a disadvantage is a smaller community. For example, Red Hat is very active with SE-Linux, and they do quite a lot of stuff there. And because of the joys of open source, it's available to everyone. So those AppArmor profiles, they live in etc@armor.d, and they are named by convention. So if you want to restrict the actions of the ping binary, then you would have a path looking like this. You can override those profiles by putting your own profiles in etc@armor.d local, and then those profiles would be used. For OpenSUSE 13.1, we currently have 37 profiles that are active by default, and we have 100 additional profiles that are not active by default. And the main reason there is that those additional profiles need some kind of configuration so they run. So it's often not very much that you have to configure, but if the normal user would just have them active by default and something breaks, then the normal Linux user doesn't know what to do. So let's have a look at the easy profile, because that's the easiest way to see how the stuff works. With include, you can include files. I think this is not a big surprise to you. And this is probably the first line you will see in every AppArmor profile. That includes the files under tunables and global, or this file. And there are certain settings like the home directories and stuff like that. So this gives you several stuffs that you can just use, and people can configure the system and the profiles still work. So for example, if someone has their home directories in a different path. Next, you specify which binary should be contained. And here we have a special syntax. So this one matches if the binary lives in bin ping and also if it lives in user bin ping. So you don't have to write two different profiles, you can write it in this way. Next we include some more files. And I counted the AppArmor rules that are in those files and added them as comments behind the lines. This is very convenient if you want to repeat some rules and you don't want to write them in every profile. For example, the last one allows you to use name services, which is kind of useful because if you want to ping a certain domain, that wouldn't work if you wouldn't include this abstraction. On the other hand, those abstractions allow quite a lot of stuff that you probably don't want for everything. So before you use this includes, you should look in the files and look what's in there. So this last line allows quite a lot of network access that you probably don't want to allow for everything. Next, with the keyword capability, we can allow certain capabilities. So with those two lines, we allow ping to use the capability net raw and set UID. Without those lines, ping wouldn't be able to use those capabilities even if they were granted to the binary. Next, we allow network access with the keyword network. And in this case, we allow raw network access. This is something that is necessary for ping, but probably isn't a good idea for other programs. So you can restrict the network access to various protocols like TCP or stuff like that, but that's pretty much what you can do with AppArmor. So SU Linux offers way more in this regard. And finally, we specify the access to the binary itself. And we do that via those flags. And don't worry, you don't have to remember all this stuff. It's only important that you have seen it once and then you can look it up online. Those flags tell you with M, you're allowed to memory map this file as executable. With IX, you specify that this binary can be executed in the current profile. And with R, you specify that the binary is allowed to be read. And also, you see that you can use the syntax that you use for the profile itself. You can also use it for the access rights on files. And last but not least, we allow it to read the file etcmodules.conf, and that's it. So this is the complete profile that is included in OpenSUSE 13.1 for the ping binary. What does it mean? So if an exploit is there that allows you to overtake the ping process while it is running. So there's some kind of trivial buffer overflow, and you get back a packet, and someone takes control of this process. Then only those accesses are allowed in here. So this process won't be able to read your etc shadow file. It won't be able to access file in your home directory or stuff like that. Only maybe if it's in those includes, so better have a good look at this. So let's get to a little bit more complicated profile. And this is one of those places where I told you about that it's not the perfect reality, because this one is used as an example, so you can have a look at many different ways of allowing access. You just can't take this and use it one by one for your foo binary. So we know the first line, we include this tunable global file. Then we specify that this will be valid for the binary user bin foo, include some abstractions, and granted the capability setGID. Then we use the network statement to allow it TCP networking. So that's the difference to the ping binary. Ping had raw network access. In this case, it's only TCP networking. With the next line, we allow it to create a link from this file to this file. So you can control very fine-grained which kind of linking is allowed. And you would need some more rules to allow the accesses on those files, but this is one of those cases where this example profile is not complete, but we only have 50 minutes. Next, we allow read access to def random and def urandom. There you can also use this syntax, so you don't have to use two separate rules. and then we allow it read access on its own configuration files. So up until now, pretty much everything is kind of straightforward. If this binary needs some kind of libraries, then you can use rules like this. You could allow only specific libraries, but this can become quite tedious. So you would have to look up which libraries are needed by which kind of program and add them one by one. Or you just use something like that allows the memory mapping and reading of those libraries, and then you're pretty much fine. So maybe you need a little bit more paths than only those, but this is the way to go forward. Next, we will see a different kind of syntax, and this one allows the reading of everything under proc that starts with a digit and then continues on. And those two stars signify that this doesn't only go to the next slash, but this matches the whole path. So with this line, you allow the reading of everything that's below proc. So listing all the information that's there. This is one that I removed, so I will skip this. With the next line, we allow the listing of the temp directory. So if you grant the read permission on a directory, then you grant this process the right to list files in this directory. With the next line, we allow it to write and to read a PID file, which you probably shouldn't put under temp. And with the next line, we allow it to link, to read and to write files that match this pattern. So you can either use the link keyword and specify the source and the target, or you can use the flag L to specify that linking is allowed. Then you get one of the benefits that you get by including this tunables file. You can use stuff like home, and this will match the configured home directories in the tunables file. So if you have a non-default home directory, then you can just adjust it once in this tunables file, and all the profiles will adjust at once. And with the specifier K, we allow the locking of a file. So what do you do if you want to execute another program from an existing process? There are several ways to do that, and I will show some of them. There are more, but those are the most important ones. So with capital PX, you allow the discrete profile execute mode. So with this rule, you would allow to execute anything that lives under bin if there is another profile that specifies the access rules for this binary. So for example, if there is a AppArmor profile for bin ls, then you could execute this binary and it would switch to this profile. You have this something very similar with the next line with capital CX, that is discrete local profile execution mode. You're able to specify other profiles in profiles, and we will see an example for that soon. So if you want to have if you want to put restrictions on the execution of a binary, and you don't want to have a global profile, then you can just define a profile local to your profile and use it with this way. And the third example is the execution of mount with capital UX. You can execute another binary in unconfined mode. So now the restriction we placed on the current profile won't match the mount binary. And of course, you have to be pretty careful with that. And the one we already know, so IX allows the execution in the current profile, so the profile won't change. All of those versions that I showed with the capital character in the first place also have lowercase versions. And the difference is that they won't scrub the environment. So sometimes it's necessary to put stuff in the environment so the other program can use it, but it's also a security problem. So for example, if you specify paths or other stuff, then this can be used as an attack vector. And because of that, it's to be preferred not to use that, only in cases where you really have to use it. So remember, we had a rule that allowed the execution of this binary with a discrete local profile. So we need this local profile, and we started with the keyword profile. This is something that you don't have to use, but you can use it to show that it's a profile. Specify the path, and then we specify some flags. And those flags can be used on any profile. And complain shows that this AppArmor profile won't be enforced. So all the rules that are specified here will be locked if they are violated, but the access won't be prevented. And this can come very handy if you want to create new profiles, because you create a basic profile, set it to complain mode, and then you get log messages that you can use to create your profile or improve your profile. So in this case, we allow it the reading, memory mapping, and execution in this current profile of bash and cat. Next, we allow it the reading, writing, and linking of files that match this pattern, and the reading of its configuration file. And last but not least, we also have a keyword R-limit. With that, we can place certain limits on the running process. So with those two statements, we would put a limit of 100 megabytes on the data segment, and we would only allow it to run with nice values equal or greater to 10. So this was the more complicated and contrived example, but this should have shown you some of the things that you can do with AppArmor. There is way more stuff you can do with it, but those are the most basic things that you will probably see if you use one of the tools that you will see soon. So if you want to create a profile, what can you do? You can write them from scratch, but that's a little bit tedious. You can adapt an existing profile, and that's probably quite a good idea because there are many. So you look what kind of profile fits the binary I want to contain the best, and then you adjust it. Or you can use one of the tools that are shipped for that purpose. So there are several tools, and I will show some of them. This is something that I wanted to skip, so I will skip it. One of the nice tools is AAGenProf. This one generates a basic profile and then sets it to complain mode. Once this profile is loaded to complain mode, every access that is tried and would be denied is logged. So then you can execute the application and afterwards log the events that happened and generate allow rules from that. So if you run AAGenProf on the ls binary, it will create the corresponding profile, set it to complain mode, and then wait for you to execute the application. I did this in this case by just listing the dev directory. You should, of course, try to provoke every access pattern that you will see in real life. So for the ls binary, that's probably not the way to go. But if you have a more complicated program, then you should use it for a while or run it for a while, collect all the log messages, and then use the program to analyze them and help you guide through the creation of the profile. Once you're finished, you press S, and then you're guided through all the log messages one by one, and you're asked if you want to allow them, deny them, glob them. That's often useful if you, for example, access files that end with the extension .log and you want to allow access for something like that. And then there are several other options that you won't need most of the time, and the man page explains them. So you go through them one by one and just tell the tool what you want to do with those rules. And once you're finished, then it creates the profile and you can use it. So it's quite easy to use, but you still have to understand what kind of access you really want to allow. There are several other tools. So for example, AALogProf allows you to scan and review the log entries. So this is useful if you already have the log entries. So maybe you created a basic profile, set it to complain mode, and after a while you realize, okay, there are still some log messages, and you can use this to go through the log messages and generate the necessary rules. You can use AA EasyProf. It's a little bit easier to use than the other tools, but the drawback is that the results might be less restrictive than with the other tools. So I personally use AA GenProf. EasyProf is a little bit easier, but if you do this, then I think it's worth the effort of just doing it right and taking a little bit more effort. And with AA-exec, you're able to launch a program in a specific AppArmor profile. So you saw that you specified a path to the binary as a key to the profile. And if you want to execute a binary in a certain profile and it doesn't match that path, then you can use AA-exec. The most important point with those tools is to always review the results. So if you just take every denial and generate the necessary allow rules, then you gained nothing. So you have to understand why you need those accesses, and you have to reason about that. Because quite often, a certain program just asks for an access or for a certain right, and it doesn't really need that. This is way more pronounced with SE Linux, but even with AppArmor, just because a tool or a program wants a certain access, it doesn't mean that it really should have it. So with that, I will switch to SE Linux. And if you thought that those profiles were a little bit complicated, then brace yourself, because now it will become complicated. So, a short history. SE Linux is also a Linux security module, and it was originally developed by the NSA. So this is great, because we all love the NSA, but don't panic. It's open source, and it's reviewed thoroughly, so there is not really a chance that there's anything in there that the NSA can use to attack your systems. And if you don't trust them, then you can look at the Linux kernel code if you can read the stuff. It was first released in the year 2000, and since then was integrated in the mainline kernel. So both of those systems are in the mainline kernel. We had a discussion during the lunch break. You can use both of those systems with any recent Linux system because it's there in the kernel. You need all the user space stuff and the profiles, but the code for both of those systems is in the kernel, so it's just a matter of a boot switch to switch from one system to another. The basic idea with SE Linux is type enforcement. So every object in an SE Linux system, or pretty much every object in an SE Linux system, has a user. In this case, I chose unconfined U as an example, has a role, in this case unconfined R, and a type, unconfined T. So first, it's important to understand that SE Linux user has nothing to do with a Linux user itself. So you can have totally different SE Linux users from the normal system users you know in your Linux system. And next thing that's important is that those naming conventions are just conventions. So there's nothing that really forces you to end a type with a underscore T, but it's good practice to do it, because otherwise other people won't understand your policy. But we're still not finished. There's more. It also has a sensitivity. So this is the way they look in a native SE Linux system. You can translate it to stuff like secret or public or stuff like that. And then there are also categories. So those are used to further compartmentalize information. For example, if you have the top secret killing of bin Laden and you have the top secret spying on all European citizens, then you can use the categories to separate those two, and even if someone has a top secret clearance, he can read only the thing that he has the necessary category. So these together form the security context. So you just concatenate all those, and then you get something like this. And this looks scary, but the first good thing for you here is you can ignore pretty much everything besides the type. So this is everything that we will cover during this talk. Everything else can be ignored, because those sensitivities and categories are not important for you pretty much ever, unless you work for the military or an intelligence agency, or are really as a Linux geek. And the user is also not very important. The role can become important, but for the most time you won't notice it anyway. So I talked already about this. Pretty much everything has a security context, and you can list those security contexts with a capital Z with most of the tools. So if you list a file and specify this flag, then you will see that this file has the type shadow T. And then you're able to control the access to everything that has the type shadow T with the SE Linux policy. But not only files, also processes have a certain type. So if you list a process and specify a capital Z, you will see that the postfix master binary runs in postfix master. I won't pronounce the suffix T all the time for the types because this can become annoying for me and probably for you. So in a normal SE Linux policy, you have 83 different security classes. And there's quite a lot of stuff in there. So you have a security context for socket, packets, for pretty much everything you will interact in a normal Linux system. And you're able to control access for all of those interactions. What's also very important to know is that discretionary access control always comes first. So if you're not allowed to list a certain directory because the normal discretionary access control doesn't allow it to you, then you won't see any SE Linux denials because it doesn't reach that stage. If it is allowed, then every access decision is checked against the security context of the source and the target. And then you look if the access that is tried is allowed for this combination. So if you have a security context that looks like this, so important part is the type, and it tries those operations on the object with the type, type 2, then you will get a check from type 1 to type 2 with those operations. You can think of SE Linux as some kind of firewall for system calls because most of the system calls that you use will generate some kind of SE Linux event. So how would you write a policy that allows the access that is displayed here? You can use basic SE Linux statements, and then you would just use the keyword type and declare type 1 and type 2. Next, you would use the keyword role and declare role 1 and role 2 and associate the types with those roles because only roles that are associated with certain types form proper security contexts, and this is pretty much everything you need to know about roles. And then you finally have an allow rule that specifies that type 1 may access a file of type 2 with those operations. So if you write an SE Linux policy that way, you will get crazy quickly because even for very simple programs, you need many, many rules, and this can go into the thousands very quickly. So this really doesn't work. Next, it's quite hard to maintain because you just have those rules and you can use stuff like you include other files to structure it in any meaningful way, but it's still not really good and easy to maintain. And the main point is it's hard to distribute the work of creating policies. If it's your full-time job to create SE Linux policies, then maybe you can do it. But if you're a normal administrator and you just need to do some adjustments, then it's just not possible for you to write a complete SE Linux policy. And the solution to this is the so-called reference policy, also often called ref policy. So this is a community project that wants to create a basic policy that you can use to extend it. And you can extend it very easily because it's modular and uses M4 macros to create interfaces. So instead of using all those SE Linux rules, you can use the interface that are already there to allow certain access types. And it also contains custom modifications for various distributions. So if you run a SUSE system or a Debian system, then files will be at different locations. And in the reference policy, there are some adjustments that only match Red Hat systems or SUSE systems. So what does it take to confine a daemon in SE Linux? First of all, you will need types for the processes that are spawned. Those are called domain types, but this is just a name for it. Those are basically normal types. Then you will need types for files that you will work with. And then you will need transition rules. And those transition rules are very important because if you think about a normal init system, so on a modern system, this will probably be systemd. Systemd will run in its own type. And if you want to start a daemon, then your daemon will have another type. And you will need some way of getting from this type to this type. So therefore, you need some kind of transition rules that allow you to go to the other type. And then you will probably need some rules to allow standard interactions. So for example, if your daemon wants to use syslog, then you can use rules that are already in the reference policy to allow it those accesses. We have several ways of creating new modules. You can write them from scratch, but this is something that I wouldn't do. This is just too painful. You can adapt an existing profile. That's a very good idea because you will see what kind of interfaces you need because there are many in the reference policy. And you can also use tools that are shipped for that purpose. And I will introduce the main one that you will probably use at the end of the talk. So if you want to adapt an existing profile, then a good place to start is the ref policy contrib repository that is hosted at GitHub. In this repository, there are currently over 350 modules. So you can just pick the one that fits the binary you want to confine the best and extend or change it. They range from under 20 lines to over 1,400 lines for Apache, which is not surprising because Apache is quite a complex beast. And those lines for the Apache module are interface calls. And each interface can easily generate hundreds of SELinux rules. So you can see how many rules there are for a complex daemon. A module consists of 3 files. First, you have .fc files. They contain rules that specify the types for the files that are on the file system. We'll see an example for that later. Then we have .if files, and they contain the interfaces that your module provides. For the most part, you won't write modules, but if you want to allow access to your types, then maybe you need to write them, but that's a little bit more advanced. And then are .te files that contain all the rules that are necessary for this module. So let's look at an easy example for a TE file. And for this example, I took the AppWatch module from the contrib repo and removed parts of it because even if it's an easier module, it's still a little bit too long to talk through here. Every module starts with the interface called policy module and then the name of the module and the version. And this version, if you work with SELinux, it's very important to remember you have to increase this version number. This is something that you probably will forget, and this can become a problem because then the new rules won't be able to be loaded. Next, we use the type keyword we already saw to create 2 types that we use. And in this case, we create a type AppWatch and another type AppWatch_exec. AppWatch will be the domain type for our process. And AppWatch_exec will be the type that we use for the binary to transition to this domain type. Next, we call the interface init daemon domain to say if our init system uses this binary, we will end up in this domain. And this is something, if you would have done this by hand, this could become very, very complicated because you need to adjust for several init systems. So are you working with systemd or another init system, and you need quite a lot of rules to allow everything that is needed there. In this case, you just have one interface call, and you also know what it's doing because the name is chosen properly. Next, we create another type, AppWatchData. This will probably be the type for our data files, and make it known to the reference policy with the interface call filestype. With this call, we tell the reference policy, we use this type to tag certain files. And this can become important if someone else wants to write, for example, a backup program. So imagine you want to write a program that backs up every file that is on an SE-Linux system. And on this SE-Linux systems, there are thousands of types. And some person wrote another module and created new types and tagged files with those types and didn't call this interface, then you have no way of just getting some rules like, let me read every file that is on the system, because you need to specify it for every type there is. There are several variations of those interfaces. So for example, if we have another type for our files that live in var run, then if we use them as PID files, it's good if we specify a different interface and say, okay, so those are PID files. So then they are treated a little bit differently. Next, we have the actual rules that we use to allow what our binary really needs. So in this case, we allow our domain type AppWatch on itself to use those capabilities that are specified here. So this is pretty similar to the stuff that we already saw with AppArmor. Next, and this one comes very handy, is a don't audit rule. So by default, everything is denied in an SE-Linux system. You need to specify everything that is allowed. But not everything that is denied should be allowed. It's the same thing with AppArmor. Maybe a certain program wants to have a permission that you don't want to give it to this program, and often it still works even if it doesn't get it. So for AppWatch, this is the case for this capability. You can just deny it, and it still will work. If you don't use the don't audit rule, you will get a log message every time AppWatch tries to get this capability. And this can become very, very annoying, because if you want to secure your system, then it's good to review your logs. And so you will get quite a lot of false positives. With don't audit, you prevent the logging and the access is still denied. With the next rule, we allow it to accept and listen on TCP sockets that have the same type as the domain. You could use a different type if you wanted to, but AppWatch uses it this way. Next, we use one of the interfaces that are in the reference policy. And the interface is not very hard to understand. It allows you to manage files that match a certain pattern. So in this case, we allow our domain type to manage files that live in directories that have the type AppWatch data, and the files have the type AppWatch data. So you can reuse a type for different classes, and that's very often done for directories where it makes no use to have two separate types. Finally, we allow it to read the kernel network state and the kernel system state with those interfaces. And they are an example of an interface that is provided by a module. So there's a module for the kernel, and the kernel provides several interfaces so it can encapsulate its implementation details. And with that, we specify that our type needs to access those information, but we don't need to know the details about how this is done. So this is part of the TE file. As you can see, there will be a lot of rules for at least a little bit more complex files, complex processes. But what's still missing is how do we get those types to work with. And for that, we have the .fc files. So with those files, we specify that certain files on the file system have a certain type. So we specify that the file user sbin appwatch will get the type appwatch exec. Gen context is another macro, is another interface from the reference policy. The most important part here is the type. You can ignore everything else again. What's important to remember is that this only specifies the initial context. So if you use a tool like restoreCon, which resets all the contexts for the files on the file system, then you will end up with a file system where the files have the types you specified here. if you then move the file to another location, or if you compile a new binary, and you compile this in your home directory, and because of that, it will get the type of files that live in your home directory and move it to this location, and you're not using the proper options, again, capital Z, then this type won't be resetted to the thing that's specified here in the .fc file. And this is one of the things that happens on SE Linux systems all the time. So if something breaks, look at the types. And if this looked tedious, then yes, that is tedious. Writing those modules is a real big pain. But luckily there's a tool, and this is called audit to allow, and it's a bit like a logprof, and I really love it because you can use it and it really suggests very good solutions to your problems. It works by analyzing the SE Linux denial messages, so if something doesn't work, then you will get denial messages. And if it doesn't work, then you will get a lot of denial messages. And then it generates the rules to allow the necessary accesses. And the very nice thing about audit to allow is that it's aware of the reference policy interfaces. So it wouldn't be of much use if it just generated the normal allow rules, because then you will still have a big mess of very many allow rules. But audit to allow knows which kind of interface is needed to allow a certain access. And it also suggests booleans. Booleans are something in an SE Linux policy that can be used to toggle certain access rights. So for example, if you have your home directory on NFS, then you need certain access rights that you usually wouldn't need. And because of that, it's usually denied in a SE Linux policy. But you can toggle a certain boolean, and with that, you're allowed to make this access. And if you have denial messages and you pipe them into audit to allow, and it realizes, okay, your home directory is on NFS, then it will tell you, hey, there is a boolean. If you turn it on, then you probably will have no problems anymore. So let's quickly look at SE Linux log messages. They are usually in the audit log. In this case, we have a denied access, and the right that was asked for is a transition. And we wanted to transition from this source context from kernel T to unconfined T. Audit to allow uses those messages and then generates the necessary rules. What's important to realize is that you shouldn't use it with every denial. So it's the same as with those AppArmor tools. But with SE Linux, it's a little bit more important because you really have to think first if this makes sense. Because if you look at the source context here, then you see the kernel wanted to transition to unconfined. And unconfined is, as the name suggests, a type that isn't confined very much. It's confined only a little bit, but for the most part, you can see it as unconfined and is used for normal users. The question is, why do you need to transition from the kernel to an unconfined user? And if you look at the binary that was executed, then you see it was my shell. And in this case, and you need a little bit of experience to know that, it was just the case that the init system was mislabeled, and because of that, it wasn't running as init T, but as kernel T. And the experience you will get through painful try and error. But so don't use audit to allow on everything you see. This will really undermine the security of your system. A quick example, because I know that I won't have much time. If you call audit to allow, then you have several ways of calling it. A useful way is described here. So if you specify B, then it reads all the denials since the last boot. So you booted your system, nothing works anymore. Let's have a look with that. And then with M, you specify that you want to generate a new module, and you can specify a certain name for that. And with -R, you specify that it should use the reference policy interfaces. It doesn't do that by default, but those are the switches that you will probably need a lot. And this will generate 4 files. This will generate a TE file, an IF file, nothing will be in there, and a .fc file. And then it will compile all of those files into the compiled module, with the extension pp. You should analyze those files. Look in the TE file if the access that is specified there is something that you really want to have on your system. And if you're satisfied with that, then you can finally load it with SE module and -I. And then it's running in your system and those denial messages should not be there anymore. So, we are through. Let's have a quick comparison. Which system is better? This pretty much depends on what you want to achieve. If you know one of those systems, then it's probably best to just stick with it. Because if you're good with AppArmor and you're working as a normal system administrator, then it's probably not worth the pain to learn SE Linux. If you're good with SE Linux, then it's probably not worth to learn AppArmor because you already have a system that can control access very fine-grained. If you work in a high security environment, so if someone wants to go to the NSA, then you probably will have to use SE Linux because you can do stuff there that's not possible with AppArmor. So all this top secret stuff can only be done with SE Linux. If you want to learn from scratch and you have some time, and I should have added and some nerves, then I would suggest SE Linux because currently it looks like, at least for some projects, the SE Linux support is a little bit better and you can do just do more stuff. What's a drawback is you can't have both active at the same time. So both are Linux security modules and you can only boot with one of those. So you can specify security equals and then AppArmor or SE Linux and then one of those systems will be active and you can switch on every boot if you like to, but you can't have them active at the same time. My personal favorite is SE Linux. With SUSE, we support and use AppArmor and the main reason there is people can actually use AppArmor. If you type in SE Linux and you have autocomplete active by Google, then you will see the suggestions disable, remove. This is the thing that people Google for. And in pretty much every entry in a forum, you will see, okay, isn't this problem? Okay, disable SE Linux. So even a system that's not as good as SE Linux, but is actually used, is way better than just disabling SE Linux with the first kind of problem that you run into. So give both a try if you have time, and stick with one of them. So thank you for your attention, and I don't know how much time we have for questions. I think
we have to save some time for questions because this was excellent. I guess that we will get some questions. So regarding AppArmor, what's the hardest process to profile?
Well, I have to admit I'm not an AppArmor expert. I learned AppArmor since I joined SUSE. I think everything that really needs fine-grained network access control can become very problematic with AppArmor. So, and also profiling quite easily, quite simple stuff like if you want to confine a local program, then you will need to specify all the file access and you need to specify this in your profile. With the SE Linux, you can use much of those interfaces and then you gain much of the accesses that you need without really needing to understand everything. But for example, if you want to confine your LS binary, well, which parts do you not want to read? So this is kind of hard.
Hi, I'm just wondering why are you allowing ping to read all the other programs' memory?
I don't know. Okay. I really have to say honestly, those are the profiles that are shipped by SUSE, and I didn't write them. So this is a good question. I am currently writing the SE Linux policy for SUSE, so maybe in 2 years I can answer you the question for the SE Linux policy. But most of the time it just works that way. You write a basic profile and confine it as much as possible, and then we use it a while in OpenSUSE, and then people start to cry because certain stuff breaks. And then we look at it, and if it's really necessary and not just eye candy or stuff like that, then we allow it. So probably there's a good reason, but without looking in our bug tracker, I can't tell you the reason.
Are there any measurable overhead in any of these systems, AppArmor or SE Linux?
Yeah, I don't know the exact numbers, but for SE Linux, the overhead was in the 1-digit percentage range. So it is measurable if you measure carefully, but I think for really security critical systems, it's not much of a problem, at least in my opinion. I mean, I'm a security guy, I don't care that much about performance. But having a slowdown by 5% is not a problem for me. Database guys will probably think differently, but for me,
I mean,
doesn't matter.
you said there were 1,400 rules just for Apache, I think.
Yeah, for that it performs very nicely. I mean, I wrote something so that you can control access with the Ruby language, so you can control the access to Ruby objects with SE Linux rules by asking the kernel. I tried that, and there the overhead was a little bit higher.
So, is SUSE 11 shipped with SE Linux turned on? No, of course not, I guess. It's AppArmor.
Well, it's turned on. I mean, it's the default system is AppArmor, and this is the default boot option. So it is in the kernel, and you can just switch, and we provide policy packages that you can use as a base, but it's not fully supported.
More questions?
And sorry for not having that many pictures. I was sitting up there and I couldn't understand a word, but I was looking at all the pictures and was thinking, well, that would have been a good idea.